A maglev brain. Have you ever thought how it is working? A doctor uses MRI scan to detect diseases. Fast digital circuits send superfast coded signal from one source point to another. Is it possible to get the information about the neural activity inside the brain? Yes, it is possible. These technologies are possible thanks to superconductivity. Superconductivity was discovered by Kamerlingh Onnes in the year 1911. He was studying the resistance of solid mercury at cryogenic temperature using the recently discovered liquid helium as refrigerant. He observed that at 4.2 Kelvin, the resistance abruptly disappeared. In subsequent decades, superconductivity was found in several other materials. In 1913, he was awarded for the Nobel Prize for his important discovery. Resistance of a material depends on temperature. When the temperature is increased, the resistance increases, and when the temperature is decreased, resistance decreases. On decreasing the temperature, it was found that at a particular temperature called the critical temperature or transition temperature, the resistance of a material called mercury dropped to zero. The temperature at which this happens is called the critical temperature or transition temperature. At this particular temperature, the material transforms from one conducting state to another conducting state. That is why it is called critical temperature or transition temperature. That is, material conducts electricity without any resistance, and conduction without any resistance is termed as superconductivity. Superconductor characteristics: resistance dropped to zero, expulsion of magnetic field lines, discontinuity in specific heat versus temperature curve, change in thermal conductivity and volume. Factors affecting superconductivity of a material: first one is temperature, second one is magnetic field, and third one is the current density. These factors decides the superconducting state of a material. Another interesting aspect of the magnetic properties of the superconductor is the Meissner effect, discovered by Meissner and Oceanfield in the year 1933. According to this Meissner effect, a superconducting material will expel all magnetic field lines. When a conductor is kept in a magnetic field, depending upon the magnetic history of the material, more number of field lines will pass through it if it is a ferromagnetic material, and few number of field lines will be passing through it if it is a paramagnetic material. But when the material is cooled in a magnetic field, on attaining critical temperature, the material turns to a superconductor, and we can see that all magnetic flux lines are expelled out of the material, which is termed as Meissner effect. The above process occurs due to the development of surface current called the persistence current, which is developed on the surface of the material. This current produces a magnetic field, and this internally developed magnetic field cancels the external magnetic field, making the flux density within the material equal to zero. Total magnetic induction inside a material is given by the Sommerfeld convention. According to this, B equal to mu 0 into H plus M. And we know for a superconductor, B equal to 0. So this equation reduces to H plus M equal to 0 because mu cannot be equal to 0. Dividing throughout by H, we get 1 plus M by H is equal to 0, or 1 plus psi is equal to 0, where psi is magnetic susceptibility, which is negative 1, indicates that a superconductor is a perfect diamagnet. So summarizing this session, we studied about superconductivity, which is a phenomena exhibited by certain materials when they are cooled below the critical temperature. Then the characteristics of superconductors, which are resistance dropped to zero, expulsion of magnetic field lines from the interior of the material, discontinuity in specific heat versus temperature curve, and change in volume and thermal conductivity of the material. Then we studied about the factors that can destroy or which can affect the superconductivity of a material, which are temperature, magnetic field, and current density. And last we studied about the Meissner effect, which is the expulsion of magnetic field lines from the interior of the material when it is cooled in a magnetic field.